Drop a pile of iron filings near a bar magnet, and you get immediate, predictable geometry. The solid metal exerts a stable, highly ordered magnetic field, snapping the filings into place along invisible curves. But if you zoom in to the atomic level of that same bar magnet, that rigid predictability vanishes. You are looking at a lattice of trillions of individual magnetic moments, vibrating chaotically under the constant influence of thermal energy. This presents an obvious paradox. How do unimaginable numbers of independently vibrating, chaotic microscopic moments collectively agree to align in the exact same direction? We are looking for the exact threshold where thermal chaos snaps into collective order. In physics, this is called a phase transition. To isolate the mechanics of that transition, we have to strip away the complex quantum mechanics of real atoms. We need to reduce the system down to its barest mathematical logic. Incredibly simple, universal mathematical rules that govern large populations of interacting neighbors. To decode those rules, statistical mechanics relies on a specific theoretical tool, the Ising model. This grid represents the core of the model. It strips a solid magnetic material down to a constraint baseline, a rigid lattice of binary variables, where each site can only point in one of two directions, up or down. Unlike other mathematical models that allow spins to rotate continuously in 2 or 3 dimensions, the Ising model's strict two-state limitation forces the system into stark, easily measurable outcomes. By imposing this extreme simplicity, the model demonstrates that phase transitions are the direct result of a mathematical war between exactly two competing physical forces. The first force is interaction energy. This is a local rule that strictly drives neighboring sites to align with one another. The second force is thermal randomness. This is the energy injected by temperature, which strictly drives the system toward chaos by flipping sites at random. Evaluating how these two forces compete across a lattice reveals the mathematical engine of phase transitions for every physical system sharing this underlying symmetry. We start with the bedrock unit, a single discrete variable, denoted as SI, constrained strictly to +1 for spin up or -1 for spin down. These binary spins are placed onto a regular geometric lattice, with every intersection hosting exactly one spin. This equation is the Hamiltonian, the master ledger calculating the total energy score of the lattice. Physical systems always seek the lowest possible energy. Looking at the core interaction term, the model evaluates only immediate, nearest neighbor pairs, ignoring distant spins completely. The letter J represents the critical coupling constant. It operates as a mathematical reward given to the system whenever two neighboring spins match. Because the Hamiltonian serves as an absolute rulebook, calculating these local neighbor interactions allows us to predict how the entire macroscopic grid will behave. This brings us to the rule of pairs. Taking our negative J constant and multiplying it by a positive one, and then another positive one, results in negative J. Proving alignment actively lowers the system's total energy. If we test anti-parallel spins, multiplying opposite spins results in a positive J. Clashing neighbors actively raise the system's energy score. Scaling this pair rule up to a two-dimensional cluster, a central spin surrounded by 4 aligned nearest neighbors creates 4 happy bonds, resulting in negative 4J. If that central spin flips, defecting against its neighborhood, the total energy change is a massive 8J. An 8J shift represents a severe energetic penalty for an isolated spin flip. Because thermodynamic laws heavily penalize moving to a higher energy state, this steep mathematical cost forces ordered magnetic domains to lock into place. But the Hamiltonian's drive for perfect order constantly competes against a chaotic antagonist, thermal agitation, represented here by temperature. While the J constant strictly enforces alignment, thermal energy acts as random background noise. It constantly attempts to flip spins back and forth, entirely ignoring the preference of their neighbors. In statistical mechanics, probability governs the grid. At very low temperatures, that 8J penalty is insurmountable. But as temperature rises, the strict mathematical penalty for high-energy clashing bonds begins to vanish. Eventually, the system reaches a high-temperature state. Here, random thermal flips become so frequent and energetic that they completely overwhelm the local J interactions, shattering the aligned domains. A magnetic phase transition occurs at a precise tipping point, where the kinetic energy of thermal randomness finally outweighs the interaction energy of the lattice. In the 1920s, physicist Ernst Ising solved this exact mathematical model for a one-dimensional chain of spins. Based on his math, he concluded that spontaneous phase transitions were impossible at any temperature above absolute zero. Looking at the 1D structure clarifies his reasoning. The boundary where an upspin region meets a downspin region is called a domain wall. In one dimension, this is just a single point of misalignment. Creating that single broken bond costs a small, finite amount of energy. Crucially, that domain wall can be placed anywhere along the entire chain with the exact same energy cost. Because of this immense positional freedom, thermodynamic entropy overwhelmingly favors creating multiple domain walls at any temperature above absolute zero. These proliferating walls inevitably slice the one-dimensional chain into random, microscopic fragments. Long-range order is destroyed the moment heat is introduced. In a one-dimensional universe, thermal entropy is an unbeatable dictator. The emergence of macroscopic order is strictly governed by the spatial dimensionality of the system. 2 decades later, Lars Onsager solved the model for a two-dimensional grid, proving that phase transitions absolutely do exist when you add a second dimension. In a 2D grid, domain walls are no longer isolated points. They become extended, continuous boundaries. Creating a long boundary requires breaking many bonds, which costs vastly more energy. This geometric constraint successfully prevents entropy from shattering the system at low temperatures. This graph charts Onsager's exact mathematical solution. It proves that long-range collective order survives the thermal noise, right up until the system hits a highly specific, fatal temperature. Notice the sudden, dramatic plummet of magnetization exactly at the critical temperature, equating to approximately 2.269 joules over the Boltzmann constant. This mathematical exercise is vital to modern science because of universality. When scientists run experiments on real anisotropic than metic materials, the data perfectly matches the 2D Ising predictions. Layered fluids, binary alloys, and expanding gases all behave exactly like the Ising model near their critical boiling points, provided they share short-range interactions and binary symmetry. By stripping reality down to a lattice of arrows, the Ising model proves that the most complex, chaotic macroscopic phenomena in the universe are ultimately driven by the most beautifully simple microscopic rules.